Let's review quickly what we said. Look into the steps before we go on to the section 8.2 on testing actual claims about proportion. So again, you're gonna see a claim about one of these parameters, either the population proportion or mean or standard deviation. And our goal is to see if the sample will support the claim or will reject the claim. So sometimes this sample is strong enough to support the claim. Sometimes it is strong evidence to reject the claim. Sometimes there is the sample is not sufficient to say anything about the claim. These are the three cases that we're going to discuss. Three types of scenarios. The claim says that the parameter is greater than. In this case, the null hypothesis, the parameter is equal. The alternative is greater. So the alternative and the claim are the same. Another situation is when the claim says that the parameter is less than, the null hypothesis says the parameter is equal, and the alternative, the parameter is less than. Another case is when the claim says that the parameter is equal, has a value equal to a specific number. In this case, the null hypothesis is the parameter is equal to the claim value and the alternative not equal. So I'm gonna show you examples on all these three cases. Once you state the null and alternative, you'll be given the value of alpha, significance level. You will use that in your calculations. These are the formulas that you're going to use to get your test statistic. And once you calculate your test statistic, you're going to use either the critical value method or the p-value method to determine whether you reject or fail to reject the null. And after that, you will make your final conclusion. This is the classical method that we talked about yesterday. And this is the final conclusion. So let's go ahead and apply this procedure to a specific claim. Joanne. All right, so (8.2) Example number 1. Test the claim using a significance level of 0.05 and sample data the claim population proportion is greater than 76%. All right. So this is a parameter, a population proportion. Let's say, for example, the claim says more than 76% of Americans, let's say, own a house, more than 76%. So here we're testing this claim about a percentage. P is greater than 76%. And we're going to use the sample to test the claim, see if we can either support the claim or we do not have enough evidence to support the claim. So let's say here in the sample, I'm going to give you two numbers. I'm going to give you X and I'm going to give you N, meaning I'm going to give you the sample size and then the number of individuals in the sample who has the same characteristic, who, for example, own a house. So let's say here, let's say 100 individuals out of 120 said that they own a house. 100 out of 120 individuals. So this is my sample, and I'm going to use the sample to come up with a conclusion and address the claim. We want to test the claim, so we want to address the claim at the end. So step number 1, I'm going to first write my claim and I'm going to use, instead of percentages, I'm going to use a decimal. So P is greater than 0.76. And then I'm going to write my two statements, the first and second one, the alternative. The null, P equals 0.76, and the alternative, P is greater than 0.76. As in this case, the alternative is the claim. Always, guys, always, when we start testing a claim, we always assume that the null statement is a true statement, with an assumption that this statement is true. Our analysis on the assumption that the null hypothesis is true. And then we carry out our calculations, and at the end, we either reject the null or to reject the null. right? Our calculations will lead us to this initial conclusion, which is either reject the null, the assumption is false, and we take the alternative, or we do not reject the null, and the null remains as a true statement. So at the beginning, our assumption is that the population proportion is equal 76% or 0.7. All right, so that's the first step. Second step, I'm going to calculate my test value. Alpha is given 0.05. Don't have to worry about alpha. It is there, so I'm going to just highlight it for you here. It's given. Our results is based on 5% error. There's a possibility that the result is wrong, 5% possibility. Step 2, I'm going to create z-test. This is a z-score, a z-value that is going to be calculated based on the sample data. Sometimes some authors, they call it as z-sample, from the sample. It comes from the sample, and it is p hat minus p over the square root of pq over. This is the formula, one of the formulas I gave you yesterday in the table. When we talked about the basics of hypothesis testing, this is the formula that I told you we're going to use to find the test value when we test claims about proportions. So we're going to use this formula here. So first, p hat is x over n. This is the sample proportion, 100 over 120. That will give me 0.83 after rounding to the decimal places. And then z-test is 0.83 minus 0.7, the population proportion. See here, P is the value of P is in the null hypothesis. Remember, null hypothesis is a true statement. So we're assuming at the beginning that the value of P is 6. So 0.83 minus 0.76, and then divided by the square root of P, which is 0.76. And then Q is the complement of P. Let's write it here. Q is 1 minus P, so 1 minus 0.76, 0.24, so 0.24, and then divided by this by n, which is the sample size 120. You have to be careful, guys, here when you get your test value, because this is a very important value. Our results depends on it. So 0.83 minus 0.76 0.0 over the square root 0.76 minus 0.24 divided by 120. Zero 390, 4 decimal digits. 1.79. I round Z values to 2 decimal places. The sample gave me this Z score or Z value. Now, in the next step, I'm going to look at the sign 1.80. I have 1.79. How did you get 1.80? Let me see. 07. Yes, if you put the complete denominator into the calculator, you will get 1.795. No problem. Let's change that to instead of 79 to 80. It's not going to make a big difference, but Jason is right. If we put the denominator completely, then it is going to be 1.80. No problem. All right. Once you get your test value, you will now use the critical value method. You're going to apply one of the 3 tests that I showed you yesterday. I look at the symbol or the sign in the alternative. See, the null has the equal sign, the alternative has greater than sign. So I'm going to use a right tail test. Right tail test. Right, very important. Why? Because the alternative hypothesis has the greater symbol. It says portion is greater than 0.76. And here's the, I'm going to graph the distribution. Z distribution. Our test value, Z test, is 1.80. That's the sample test value. That's what we got from the sample. Now I want to calculate Z critical. Since we're going to use a right tail test, Z critical is going to be a Z value that corresponds to an area in the right tail, and that area is alpha, 0.05. Oh. Again, a small error, guys. I apologize for this. That should be H1. Yeah, H1 is P is greater than 0.76. So I'm going to find Z critical. That value Z critical is based on alpha. So always keep in mind Z critical comes or based on alpha. Test value is based on sample. Your critical value is calculated based on the significance level. your test value is calculated based on your sample data. Now, how do I find Z critical from alpha? I use inverse norm because I'm trying to find a Z value from an area. So inverse norm, and inside the inverse norm, I put the area to the left. What is the area to the left? It is the area to the right of that critical value is 0.05. Area to the left is 1 minus 0.05, which is 0.95. Let's see what it is. Inverse norm, 0.9501 for the mean standard deviation. You calculate 1.64. Okay. So look what I'm gonna do, guys. The test value is greater than the critical value. So I'm gonna change its location. Look, I'm gonna erase this. And my test value is 1.8, is inside the right tail. It is greater than 1.64. Z test is 1.80. So it falls inside the right tail. It falls inside what we call the rejection region, because once it falls here in this right tail to the right of the critical, that means, so we're gonna write here Z test is greater than Z critical. Therefore, reject the null hypothesis. Reject the null. Does everyone see why I rejected? You know, if the test value falls, if it's greater than the critical, it exceeds the critical, then we reject the null. Now, what does that tell us about the claim if we reject the null? So last step, final step. Let's see here. Let's logically think about this. A question from Samantha, where did the 0.95 come from? When you use inverse norm, you always put the area to the left of the Z value that you're. So if alpha is 0.5, that's the area to the right, then the area to the left, this area here, is what? 1 minus 0.05. And that will give me 0.95. Inverse norm, in parentheses, area to the left of Z value, 1.64. You're welcome. So now we got our initial conclusion. That we're gonna reject the null hypothesis. Let's go back to our two statements. Okay, so null hypothesis says that P is equal to 0.76. We're gonna reject this statement. The assumption is false, not true anymore. And because this is false, we're going to replace it with the alternative hypothesis. We're going to take this one, the alternative hypothesis. But if we take the alternative is the claim. So that means we're going to take the claim. We're going to say that we have enough evidence to support the claim. The sample is telling us to go and accept the claim. That means the sample is evidence in favor of the claim. So at the end, we're going to say there is or the sample gives a strong evidence in favor of the claim. This is acceptable, or if you want to use the wording that I gave you earlier, you will say that there is sufficient evidence to support the claim. And that's it. We're done with testing the claim. Okay. Guys, this is what we call the classical method. Now, with the advancement of computers and technology, researchers use a different method that is called the p-value method. The calculator will give you a p-value, or you can do hand calculations and get your p-value. Here it is. I'm going to take a picture of this chart. All right, so basically the technical definition of a p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic. Meaning we wanna, the p-value is the probability the sample that we have, the probability base. Remember, we said that we have an assumption. Based on that assumption, we're calculating the probability of, we have the sample and we're calculating the probability of getting such a sample, right? So if the probability of the p-value is low, which means the probability of the sample is low, that means we will reject the null hypothesis, because usually when we get a sample, the sample is always close to the center. But if it's far away from the center, that means the center of this is not correct. So this chart here is going to tell us how to get this value. I'm going to show you just a hand calculation, and then the calculator or any computer program that you use will give you that p-value. So this chart tells you first, what type of test are you conducting? In this case, we're conducting a right tail test. Right tail test. If you want to get the p-value and using a right tail test, then the p-value is the area to the right of the test statistic. It is the area to the right of the test statistic. We don't have to state the original claim. Oops, why did I do this? Yes, we do. There's sufficient evidence to support the claim. No, you don't have to. Just say there's sufficient evidence to support the claim, and that's fine. So the p-value is the area to the right of the test statistic. Okay, so here's our distribution, and we're gonna find this to the right of the test value. So we're gonna draw our distribution. Test value is 1.80, and then we're going to calculate the area to the right of this test statistic. How do we calculate an area from the z value? We use what this area is, normal CDF from 1.8 to infinity. 1.8 to infinity. It extends all the way from 1.8 to infinity. So let's see what that value is. Distribution to 1.89999. Enter, and you get 0.0359. Now, once you get the p-value, using normal CDF, you're going to compare the p-value to the significance level. If p-value is less than alpha, the significance level, then reject the null. If p-value is greater than or equal to alpha, Correction, guys. The equal sign should be with the other statement. If the p-value is less than or equal to alpha, reject the null. If the p-value is greater than alpha, fail to reject. So in this case, our value is 0.0359, which is obviously less than alpha is 0.05. So reject the null hypothesis. And because we're rejecting the null hypothesis, we're gonna take the alternative, and we say again, there is sufficient evidence to support the claim. Exactly the same conclusion that we got from the critical value method. Same result. Okay, so you can get your p-value from this chart here, depending on the test, and you compare your p-value to the significance level. If it is lower than the significance level, then it means your sample is way farther to the right, away from the center, this is very unusual. That means the center of your distribution is not where you assumed it is at, and therefore that indicates that your parameter is higher than the claimed value, and therefore you accept the claim. We accept the claim that the population proportion is higher, greater than whatever the value is, in this case 0.76. There's sufficient evidence, strong evidence, to support the claim. Any questions, guys, on this? Okay. I want to share my screen and I show you how we're gonna get our p-value from the calculator. All right, guys, so press the stat key. Move your cursor to the right to tests, and then go down to one proportion Z test. One proportion Z test. Select this command. All right. Now, you're going to put the claimed value of P. This is the value that you see in the null hypothesis. We said P is equal to what? 0.76. That's the claimed value. P The claim says it is that P is greater. The null hypothesis says P is equal to 0.76. And then you're going to enter the which is the individuals and the sample that have this characteristic. We said what, 100, what was it, 100, I think. Do you guys agree with that? Yes, and then N is 120. X, N, and the value of P in the null hypothesis. And then what type of test do we did we apply? We applied the right tail test. The claim says P is greater than the claim value. So enter. And then skip the color, don't worry about the color, and then calculate. We got 1.88. Is that true? What was the X value? One point 88, 120. Stat, calculate. That's weird. One prop Z test. 0.76, 100, 120. Let me use the actual the calculator that I have. I think there's a problem here with the software. Just 1 second, please. Press the stat key, go to tests. .76, 100, 120, greater than, calculate. Let's see here. I believe, guys, there's a little bit of difference because our test value, we used only 0.83, and the calculator is using 0.83333. So this is will give us a little bit of difference here in our test value. Let me check that. If I use more 0.83333 minus 0.76 and then divided by the square root 0.76 times 0.24 over 120. Yes, yeah, it is just because we rounded our p hat to 0.83. It is a rounding difference, right? No mistake in our hand calculations. It is just a rounding difference. Because we rounded the our p hat. But if you look, guys, 1.88, that's our test value. Still, it is bigger than the critical value, 1.64. The p-value is 0.0299, which is lower than the significance level. So same result, we reject the null hypothesis. We reject the null hypothesis, and that means there is sufficient evidence to support the claim. Does that make sense, guys? You understand this method? Okay, so let's go ahead and go back to the tablet. Questions? All right, let's look at another application. Example. I'm using one of the exercises in the section. Example 2. The company drug tests success provides one panel THC test for marijuana usage among 300 tested. So the problem is giving us the sample data. N is 300. Among 300 tested subjects, results from 27 subjects were wrong. So X is 27. 27 out of 300 got wrong test results, either false positive or false negative. Use a significance level of 0.05 to test the claim that less than 10% of test results are wrong. Less than 10%. So the claim says the population percentage or proportion is less than 0.1. All right. Proportion of wrong test results is less than 10% or 0.1. So this is the claim, the null hypothesis, P equals 0.1, and the alternative, P is less than 0.1, which means the same as the claim. Okay. Let's calculate. Alpha is given 0.05. Let's find our test value, Z test. Which is P hat minus P over the square root of PQ over N. So what is 27 over 100? What is P hat? 27 over 300. 0.9. Subtract 0.1. Then divide by P is 0.1. Q is the complement of P, which is 0.9 over 300. So the numerator is negative 0.01 over the denominator, square root of 0.1 times 0.9 over 300, and then divided by the answer. I get the whole, guys, negative 0.58 after rounding to 2 decimal places. My test. Okay. What type of test do I apply? Left tail test, right tail test, or two tail test? Where is our critical value going to be? Anyone would like to share? Yes, Sandra, excellent. Left tail test. Again, left tail test. Reason, because the alternative hypothesis has the less than symbol. P is less than 0.1. Left tail test. So that means our critical value is on this side. The area is in the left tail. The area is equal to alpha, which is 0.05. And we want to find our Z critical. Which is inverse norm. Inverse norm. The area to the left is 0.05. I'm using inverse norm. I get negative 1.64. But guys, look at our test value. Test value is to the critical. It is not more negative. It does not fall in the left tail. Test value is right here. Z test, negative 0.58. So doing a left tail test, and the test value is not less than the critical value, is not more significant than the critical value, meaning more negative. If it doesn't fall in the shaded area, then we're going to say what? Fail to reject the null hypothesis. Fail to reject the null hypothesis. Okay, and so what about the claim? What is the final conclusion? Let's look at again and try to understand this. We assumed at the beginning the null hypothesis is the true statement. We conducted our calculations, and at the end we said we're not going to reject the null hypothesis, fail to reject the null hypothesis. And the claim says no, it is less than, but the null says equal, and this is now still true. The equal sign is still true. What do we say about the claim? There is no sufficient evidence to support the claim. The sample is not strong enough to reject the claim and replace it with the, to reject the null and replace it with the claim. Do not have sufficient evidence for that. There is no there isn't sufficient evidence to support the claim, which is that less than 10% of the test results are wrong. Okay. Any questions? Let's go and use the calculator and see if we get the same result using the p-value. Use the same function, one prop z test. So go to tests, one prop Z test, put the value in the null hypothesis, 0.1, enter X, which is 27, N is 300, and then choose the less than claimed value, left tail test, and then calculate, and you get negative 0.58. That's our test value, and the p-value is 2819, and this is obviously greater than alpha. Alpha is 0.05, so to reject the null hypothesis and the same conclusion. No sufficient evidence to support the claim. Question? Are you guys with me? Does that make sense? Okay. All right. So the next topic, we're going to apply this procedure for testing a claim about a mean. Very similar. The procedure we're going to apply, this null hypothesis, alternative hypothesis, the test value, the critical value, reject or fail to reject the null, and the conclusion. Except the calculations are slight, or the formula that we use is different in this case when we test a claim about a mean. So section 8.3. Testing a claim about a mean. Claim the mean, the population mean is greater than 75. Let's say the claim says that the average test score on a specific test is greater than 75. Sample, we're going to give you the sample mean, X bar is 80. And we're going to give you the sample standard deviation, S, let's say 3, and we're going to give you the sample size 25. So we selected 25 test scores. We found that the average or the mean test score is 80, standard deviation of. Let's see whether this sample is going to support the claim that the mean score for all the tests is greater than 74. Let's see if that sample is strong enough to support that claim. or if it is not, no sufficient evidence to support. Okay, so let's go ahead and start the claim. The mean is greater than 5. The null hypothesis, the mean is equal to 75. This is our assumption that the mean is 75, and then the alternative, the mean is greater than 7. Okay, and then we're gonna calculate our. I forgot to give you guys alpha. Let's 0.01. Let's change a little bit here. Alpha is 0.0%. The next step, I calculate, since I'm testing a claim about a mean, then I'm going to calculate a t-value, t-test. And the formula for calculating the test value is, I gave you those in chart, which is x minus the mean over s divided by the square root of n. Okay, so let's calculate x bar t minus 75 over 3 divided by the square root of 25. The numerator is 5, and the denominator 3 divided by 5 is 0.6. So 5 divided by 0.6 is 8.33. Okay, 8.33. That's our test value. I'm going to do a right tail test, since the alternative hypothesis has the greater than, says that the mean is greater than the claimed value. So it's t distribution. Right tail test. Alpha is 0.01, and I'm going to find my t critical, which is in this case inverse t, not inverse normal. This is a t distribution, so inverse t, and then inverse t. We're going to put two numbers. We're going to put the area to the left, which is 0.99, right? And we're also going to put the degrees of freedom. When you use inverse t, you put area to the left of the t value that you want, and you put degrees of freedom. In this case, 24. Right, so let's use it. Inverse t, area is 0.99, degrees of freedom is 24. Right, and then paste 2.49. right? So our test value is 8.33. Clearly, our test value is bigger than our critical value. So our test value falls in the right tail, t-test 8.33. It is exceeds our critical value. So in this case, we're going to say what? Reject the null hypothesis. Right? Test value is inside the right tail. It is higher than the critical value, so reject the null, which will lead us to say that there is sufficient evidence to support claim. Okay. Now, I want to show you how to get the p-value from the calculator. And we're going to use the p-value to verify our conclusion, to verify our result. See, our result says reject the null. There is sufficient evidence to support the claim. We're going to get the p-value and compare it to the significance level. So go ahead and press the stab key. Right? Press the stab key, go to the right, and scroll down to one second. T-test, number 2. T-test. Select this function. Go to the right, highlight stats, enter the mean in the null hypothesis, mu naught, enter it, which is 75. Enter the sample mean from the sample, 80. Enter the standard deviation, 3. Enter the sample size, 25. Select the greater than symbol because we're doing a right tail test. And then go down to calculate. You can see that your test value is 8.33. That's the value that we calculated. And the next to it, below it, you have the p-value, which is 7.6 times 10 to the negative 9. That's an extremely small p-value. 0.00008 zeros, 4, 5, 6, 7, 8, and then 7, 6, which is obviously much smaller than 0.01. So result, reject the null, and we have sufficient evidence to support okay. Guys, were you able to get the p-value? P-value is okay to find from the calculator. Want me to share the screen and show you? Okay. All right. So press the stat, go to tests, t-test, second one. Enter. We do not have data, we have stats. I gave you the sample mean, sample standard deviation. So you have the stats, so select that. And then enter the mu naught, that's the value in the claim. The claim says that the population mean is greater than 75. The null hypothesis, we said mean to 75, and enter. The sample mean is 80. Enter. 3 for the standard deviation. The sample size is 25. And then select greater than. And then go down to calculate, enter. And you can see here our test value 8.33. And see here how small this p-value is, 7.6 times 10 to the negative 9, which is much smaller than alpha. You have 8 zeros before the 7.0008, which is less than alpha. The mean, the p-value is less than alpha, so reject the null hypothesis. There is sufficient evidence to support the claim. All right, guys, any questions on this? I haven't showed you yet two-tail test. I showed you right tail, left tail test. So my last example will be on using two-tail test to test the claim. Example. All right, so this is an example. It says data set 21 earthquakes, lists earthquake depths, and the summary statistics are so the sample N is 600, X bar is 5.82 kilometers. That's the average depth in the sample. Sample standard deviation is 4.93 kilometers. Use significance level of 0.01 to test the claim of a seismologist that these earthquakes are from a population with a mean that is equal to 5 kilometers. The claim says the population mean is equal to 5 kilometers. We're gonna test this claim. So to test this claim, my null hypothesis, again, as usual, the mean equals the claim value. But what about the alternative? What is it in this case? The mean is not equal to 5 kilometers. All right, so with every time the claim has the equal sign, then the null hypothesis represents the claim, same as the claim, and the alternative is the opposite of the claim, the complement of the claim. So the claim says equal, the alternative not equal. If we reject the null, we reject the claim. If we fail to reject the null, we fail to reject the claim. We're not going to say support, sufficient evidence to support, or no support. We're not going to say that. This is a case that's we're going to apply a two-tail test. And the conclusion is slightly different from the conclusions that we used earlier when we said support or no evidence to support the claim. So let's go ahead and first get our test value. T-test. X bar minus the mean over S divided by the square root of N. X bar is 5.82 minus the population mean over S, which is 4.93 over the square root of 600. So let's see what we have. 5 minus 5.82. Or actually the other way, 5.82 minus 5, positive value, divided by 4.93 over the square root of 600. .07 Guys, can you still hear me?
Watching TikTok.
Are you guys still with me? Okay, good. 1 second, please. Sorry about this, guys. For some reason, I lost the internet connection, so I'm back. So I calculated my test value. Now I'm trying to find my critical values. And I'm gonna find my critical value based on alpha. Alpha is 0.01. Now the area in each tail is alpha over 2. So 0.01 over 2, that's 0.005. The area in each tail. Okay. So I have two critical values. I find one of them, the negative value, and then the other value on the right is just the opposite sign, the positive value. So here I'm going to use inverse T, and then I'm going to write the area to the left is 0.05, and then put the degrees of freedom, which is what I have. N is 600, degrees of freedom is 599. So I'm using the inverse T. Area is 0.005. Degrees of freedom is 599. Negative 2.58. And the other side, the positive value is 2.58. All right, so these are my critical values. Now my test value is 4.07. 4.07 exceeds, is greater than the positive value, critical value. So my t-test is inside the right tail, inside the region. It's greater than the positive critical value. Therefore, I'm going to reject the null hypothesis. Right? Since the test value is in the critical region, I'm going to reject the null. So what should I say now about the claim? If I reject the null, as I said earlier, the null and the claim are the same. So if I reject the null, that means I reject the claim. Therefore, there is sufficient evidence to reject the claim. Right? We're not going to say support here. The claim is the same as the null. They are the same. Since we are rejecting the null, automatically we're rejecting the claims. There is sufficient evidence to reject the claim. Any questions? The last thing, guys, is we're going to test a claim about the population standard deviation. Again, very similar procedure. So let's do this quickly before we conclude. Final example. Testing a claim about standard deviation. Example. Test the claim that the population standard deviation is less than 2.5. Use sample data. I'm going to give you the population, the sample standard deviation, 2.3. I'm going to give you the sample size, 16. I'm going to give you the sample mean, which is 20. And alpha is 0.05. Okay. All right, so let's go ahead and test the claim. Sigma is less than 2.5. The null hypothesis, sigma equals 2.5. The alternative hypothesis, sigma less than 2.5. These are my null and alternative hypothesis. Now, because I'm testing a claim about the standard deviation, I'm going to calculate chi-squared test value. I'm going to use the sample to calculate my test value, which is n-1 times s squared over sigma squared. Okay, n minus 1, so 15, since n is 16, so 15 times s, we 2.3 squared over sigma 2.5 squared. Fifteen times 2.3 squared divided by 2.5 squared. 12.696. Just check again. Two 2.5 squared. Okay, so that's my test value. Now I'm gonna get my critical value. I'm using the chi-square distribution, which is skewed to the right. Apply a left tail test. We have chi-squared critical. Area to the left of this critical value is alpha, which is 0.05. I'm going to use the chi-squared standard table. Degrees of freedom is what, 15, so row 15. And then area to the right is, since the area to the left is 0.05, then this area to the right is 0.95. So I go to this column, 0.95, and row 15, and I get my chi-squared critical. Which is, let's see guys, I gave you the table yesterday in the lecture. Okay, so column 0.95, and row 15. $7.261, 0.95, and row 15, 7.261. So that's my critical value. Test value is not in the left tail, is not to the left of chi-squared critical. Chi-squared test is 12.696. So it is not in the left tail. So therefore, fail to reject the null hypothesis. Fail to reject the null. That means our null hypothesis is still valid, still true. Our assumption is still good. And that means there is no sufficient evidence to support the claim because the claim says that the standard deviation is less than. But the sample evidence is not strong enough to say that. So no sufficient evidence to support the claim. Yes, yeah, thank you. 7.261, yeah. Is that okay, guys? You are you with me on these examples? You understand them? Okay. Again, the general procedure is the same for all claims. You always need to look at the sign in the alternative hypothesis. Based on that, you use the either right tail test, left tail test, two tail test. You your test value with the critical, and based on that, you either reject or fail to reject the null, and then based on that, you address the claim.